Hello everybody, my name is David Moxey. I'm one of the lecturers here at the University of Exeter, where I work in the Department of Engineering. Before I get started with my presentation and the slides that I want to show you today, I thought I'd say a quick virtual hello to everybody. I know it would have been brilliant if we'd been able to talk in person and meet in person. I certainly would have liked to run a little bit more of an interactive lab than I'm currently able to do so. But as you can see from working in my house here, I'm all socially distanced just like the rest of you, and with the whole coronavirus situation, it's really a shame we can't do that this year. However, I hope you do enjoy the presentation today, and I certainly hope you enjoy the rest of the events that we have hosted for you here today. So the title of my talk today is What is Turbulence and How Does it Work? So my area of research is a field called fluid dynamics. So I look and investigate the properties of fluids, i.e. things like liquids and gases as they evolve in time. And one of the most important phenomena that lives in a fluid is turbulence, and you can see one example of that in this really nice picture here. These are all the turbulent eddies. I'm going to explain what those are later on, that shed, that you don't necessarily see because air is clear, but they shed from a car as you're driving along. And in this case, this is a kind of typical sports car, and so what we'd like to do is improve the efficiency of the vehicle by controlling all of these vortices and all these eddies that get shed, all these complicated fluid dynamic structures, so that we can improve the downforce of the car and make it maybe corner quicker and reduce the drag so that in a straight it could travel faster. So the idea of today's talk anyway is to give all of you some kind of introduction to turbulence and just tell you a little bit from a very, very high level about what turbulence is, and moreover why understanding it could have a big impact on the things that we do in our everyday lives. So what are some other examples that kind of demonstrate the importance of turbulence in everyday life? Well, if you go back to aviation for a second, it's not just getting a bit uncomfortable on planes when they get a bit jostly, it's also about making more efficient planes. So here you can see an example of weight turbulence. You've got two vortices, so big regions of spinning air that are being ejected off the back of a plane as it travels, and those are really, really strong. So things like that and minimizing those vortices, minimizing the strength of those vortices, can help make the plane more efficient, burn less fuel, help with our climate problems, and more generally, actually, understanding turbulence helps us to understand climate change. The atmosphere around Earth is full of turbulence at all kinds of different levels, from the generation of clouds and the generation of raindrops in those clouds, in fact, all the way through to huge currents of thousands and thousands of miles long. So if we can understand turbulence a little bit better, it can help us understand climate change from a number of perspectives. Some things you might not think of are mixing. So when you're trying to mix, let's say, two different chemicals, or you're trying to mix in food preparation lots of different ingredients, and you want to get a really homogeneous, uniform mix of all different ingredients, you need to know actually how to encourage turbulence, because turbulence is the thing that's actually going to make that thing uniform at the end of it. So if we don't know how to develop the turbulence, we might not be able to get really uniform mixtures of various chemicals and ingredients. Beyond that, things like your heart, where the velocity of the blood that's being pumped through your heart is very fast, is often turbulent, or maybe in certain areas turbulence would be a bad thing. So understanding turbulence can help in biomedical applications of your heart, also of your lungs, and any part of your body really that contains a fluid, which is pretty much all of it. And then finally, outside of Earth completely, you have the realm of things like stellar phenomena. So this is an absolutely massive coronal ejection from a star here. And all of those plasmas, those really superheated gases, they also have turbulent properties, just like fluids would. And so understanding turbulence really could give us a lot of insight into the behavior of stars and being able to predict all kinds of stellar phenomena. So how difficult is turbulence to really understand, and how important really is it? I'm not usually one to include quotes in my presentations here, but there's a really good one from a very famous physicist called Richard Feynman. And in those, he says there's a physical problem that's common to many fields. It's very old and has not yet been solved. Something left over from a long time ago of over 100 years. And it's the analysis of circulating or turbulent fluids. So that should give you an idea of the kind of timescale that we've been looking at turbulence. It's over 100 years since some of the first experiments, which I'm going to talk about later. And it's still one of those problems that we don't really still understand. So what does a turbulent flow actually look like? Those are some pretty complicated examples. Let's go back to something a lot simpler. So let's consider a fluid that's going to flow from left to right in this figure, just around a cylinder. So as I play the movie, what you're seeing here is the fluid flowing left to right, and you can see all the little particles being trapped in the fluid. You can also see what we call streamlines, which are essentially the path of the fluid as it goes over the top of the cylinder and then back down the other side. And so you have this really nice ordered behavior. So at very low speeds, the fluid actually isn't turbulent at all. It's called a laminar flow. So by laminar here, we mean that the fluid is ordered, it's steady and predictable. We know the path that it's going to take almost before, we can predict basically where the fluid particles are going to go. So the streamlines that we have show the trajectory of the fluid as it goes left to right, and we can almost analytically, i.e. with pen and paper, we can work out what the shape of those streamlines is going to be. So things get more interesting though as you start to ramp up the speed of the fluid. So let's make it a little bit faster. So when we do this, we can actually plot arrows now that show us the direction of the fluid in all the parts of the domain. And then as the fluid comes over the top of the cylinder here, it has this big wake behind it. So you'll see this if, for example, you look at a bridge or a pillar in a piece of water, you'll see a wake behind a pier as the fluid goes past it. So in this case, the hotter the color, the faster the fluid is going to be. And if we wait long enough here, we're going to start to see something interesting begin to happen as we make the fluid faster and faster. So let's increase the speed a bit more to see what's actually going on here. So as I play this little movie here, what you can see is the same thing that we saw before, just with a little bit less detail, so it's easier to see the phenomenon that's happening. Essentially, the fluid's going over the top. We have this little wake region behind the fluid, and then all of a sudden, you start to see this shedding motion. And these objects that are being cast off from the top and the bottom of the cylinder here are called vortices. And you can think of a vortex as something like a whirlpool in your mind. It's something that basically the fluid rotates round and round. It's kind of rotation within the fluid. And this is actually a very special kind of vortex shedding. It's called a von Karman vortex street. And these are some of the first simulations or experiments that were done with fluids to see some of this really interesting behavior that they generate. And this kind of stuff eventually leads to turbulence. So if we ramp up the fluid speed even more, what we see is that the fluid starts to become turbulent. We have a lot more chaotic motion here. So we have a lot more complicated dynamics. Things are kind of looking really, really wispy, and there's lots and lots of different little vortices being shed all over the place. One thing we can see though is if you look carefully, those big von Karman vortices are still present, but they're just a lot less well defined. And actually, if you look at a full three-dimensional simulation, not just seeing like a cross-section like we were before, but in the full three-dimensional space, you can see rather a lot of complicated behavior. So just to prove that things like that actually help us in the real world, here's some satellite imagery from the Earth Observatory, which you can find at the link at the bottom of the screen there. And to give you some context here for scale, this is an island in the Pacific Ocean that I'm not going to pretend that I know how to pronounce, and that is about 35 kilometers long. So the vortices that are being shedded here, and you can see them very clearly, that are the same kinds of vortices that you saw in the previous problem, happen at massive scale, not just in the lab or in a computer simulation, but in real life and at a very big scale. So understanding that kind of process can really help us in all kinds of problems. So we've seen some examples now of turbulent flows, but what do we mean more specifically by turbulence? Well, actually, it turns out to be a lot easier to define what's not turbulent first. So what's not turbulent? Well, laminar flow isn't turbulent. By laminar flow, we mean that the fluid travels smoothly in layers. So you can see a little channel or a little pipe here where every layer of the fluid travels at a slightly different velocity to one another, but they don't mix together. Those layers always remain parallel with one another. To the observer then, laminar flow is so smooth that you might even see any motion. So, for example, if you go onto YouTube and have a look at some laminar flows, they actually look perhaps like they've even been computer generated because they look so static in time. But in reality, the fluid actually is flowing through those things. There's also very little resistance in laminar flow. So it's quite easy to pump fluid down a pipe if it's laminar. But as we're going to see in a second, if it's turbulent, it becomes quite a lot more challenging. So in turbulent flow, here's a kind of idea of what's going on, but there's a lot of rotation, a lot of unsteadiness. All these paths now are kind of diverging from one another, and this leads to kind of chaotic or unordered motion. The motion of the fluid, if you look at it, is really clear to the observer. So you can see this yourself if you go and turn on your kitchen tap or something. If you keep the velocity, or you just tweak the tap a little bit just to start the tap going, you're probably going to see that the fluid looks lovely and laminar and smooth. But as soon as you crank up the tap and make the flow come through the tap much faster, that's going to start to have all kinds of unsteady motion in it, and that's when it becomes turbulent. There's also a lot more resistance. It takes a lot more energy to move the flow, and that's one of the other reasons that we're interested in flows being laminar and not turbulent, because if we're trying to pump something down a pipe, we prefer to have that take as little energy as we could. So methods for controlling turbulence for things like pipe flow then are quite important. Okay, so I've been skirting around this a little bit, but unfortunately there is no really one precisely defined definition of turbulence. One of the big challenges we have is actually figuring out what it means for a fluid to be turbulent, and you can almost say that you know it when you see it. That's really a very scientifically unsatisfactory answer though. So we do have some of the real hallmark characteristics of turbulence, and let's kind of talk about those. So the first characteristic is what we call chaotic motion. And probably you might think of something like chaos theory, and we talk about that all the time in movies, and the butterfly effect and all of that kind of stuff. But there's actually a more formal definition of chaos. So if you have some kind of system and you have two particles that start closely in that system to one another, and you let them run over time, it's chaotic if they tend to diverge over time. So here's a quick example. This is something called the Lorentz attractor for those that are interested, but it demonstrates something, this principle of chaos. Those two particles, you can see they start very, very close to one another. But eventually, if we leave this to run for long enough, they start kind of whizzing about all over the place, sometimes following each other, sometimes not. And that kind of ethos of chaotic motion is something that we see too in turbulent flows. The second property is what we call turbulent eddies. Eddies are essentially vortices. They're swirls that appear at lots of different sizes throughout the domain. So if we look at this really nice video that shows you essentially a vortex traveling through the air in a kind of cross section of that vortex, you can see these turbulent eddies kind of traveling through, breaking up lots of different turbulence and breaking down into lots of other smaller eddies. And if we actually kind of stop and look at the size of those eddies, then we can see that we get some large ones, some medium-sized ones, and some even smaller ones. And that is actually a really critical property of turbulence. The fact that you have lots of eddies that are of different sizes, but they behave in moderately the same way. So a final characteristic of a turbulent flow is diffusion. So when we have all these eddies of different sizes, they break up over time via a diffusive process. And diffusion is the method through which, for example, if you mix two fluids, they eventually diffuse into one another so that you have one homogeneous or uniform mix. So there's a really good example of this that I certainly remember from my chemistry classes, where you can drop little droplets or crystals of potassium permanganate into water, and you can see the little eddies forming there as the potassium hits the surface. And if we wait around long enough, then what we'll find is that once we kind of put all the potassium permanganate in and we maybe shake it around a bit, those eventually combine to form essentially a uniform solution with the water. So probably the defining characteristic of turbulence, though, is what we call the energy cascade. So you can imagine that we have these swirls that live in our fluid, and initially they start out to be quite large in size. Then what we can observe is that as the fluid kind of evolves, those large eddies start to break down into smaller eddies, and in fact those eddies then start to break down into even smaller eddies themselves. And eventually what we find is that the viscosity of the fluid, which is its internal resistance to its own movement, causes those vortices those eddies to dissipate into heat. And this is what we call the energy cascade. So the process of breaking those eddies down into smaller and smaller eddies takes energy from the really big scales. And by energy, I mean kinetic energy, i.e. the energy due to movement. and it breaks those down into smaller and smaller eddies until they reach a size by which the viscosity of the fluid takes over and dissolves them completely into heat. And this is something that we see referred to in the literature as the Kolmogorov length scale, which is named after one of the most famous fluid dynamicists who discovered and characterized this process, Andrei Kolmogorov. So that process actually ties into another really fascinating phenomenon that, as a former kind of mathematician, I find very interesting, which is called self-similarity. So you might have heard of fractals. If not, there's a link down there. You can go and check this out. But self-similarity exists in these things called fractals, where we can kind of take this fractal object and we can zoom into it. And what we find is that as we zoom into this fractal, we start to see copies of the fractal, of the original fractal at the original level, even down at very, very, very tiny scales. So in many ways, what you see in fluid dynamics and turbulence is the same. We start out with very, very big eddies, but if we were to zoom into that fluid and go down to very, very small eddies, then we'd see the same kind of size of eddy at that really tiny scale. So this self-similarity is a very important property of fluids as well, and something that you might want to go and check out if you've never seen these fractals before. So now we can probably identify some of the characteristics of turbulent flows. So we know they're unpredictable, we know they're chaotic, we know that they're essentially really swirly at lots of different length scales. We know there's some diffusion going on there, and we know that we need constant energy to sustain that, because if we were to not put any energy in, then it can't go through our cascade to eventually dissipate. So if we don't put energy into the system, eventually all of the turbulence decays and we just end up with a completely stationary fluid. But there's still a lot of open questions in doing this, because these are all just properties of a turbulent flow. We don't really understand anything about them just by observing them necessarily. For example, how does turbulence even form in the first place? And why do eddies exist? And why do they break down? These are fundamental fluid dynamics questions that we don't necessarily have the answer to. So if we really want to understand turbulence, maybe we should just apply a really simple principle. These are all pretty complicated problems. Why don't we just consider the simplest case we can think of? Well, actually, we did that. In fact, we did that over 135 years ago. This is a photo of Osborne Reynolds, which is taken around 1885, so some 135 years ago now. And in his studies, what he was interested in was, so it's probably the simplest setup that you can think of. You take a straight pipe that has no bends in it at all, you make it as straight as you possibly can, and then you make it as smooth as you possibly can as well, so you make sure there's no kind of any roughness on the inside of your pipe, and you push fluid down it, and then you see what happens. So the question is, what do we have to do to make that flow go from something that's nice and laminar to something that's turbulent and chaotic? And can that help us understand what turbulence is and how it forms and some of the properties? The problem is that a lot of that is still an open question even now. So what I'm going to show you in the rest of the slides today is some of my contributions that I did as part of my research as a PhD student, which I think gives a tiny little insight into some of this stuff, but there's an awful lot of questioning still to do. So what makes pipe flow turbulent? Well, if you look at Reynolds' original paper, and he has these fantastic figures, this is from, remember, 130 years ago, these are all hand-drawn figures of what he observed at the time. He said that when velocities were sufficiently low, i.e. when the speed of that fluid was low, if you put a little bit of dye in there, the streak of that colour will extend in a beautiful straight line through the tube, as shown in figure 3. So at slow speeds, you're getting this nice laminar flow. The dye that you can use to visualise the fluid just kind of proceeds along one of those layers we saw earlier. As the velocity was increased, though, by small stages, at some point in the tube, always at a considerable distance from the trumpet, which is the intake there, the colour band would all at once mix up with the surrounding water and fill the rest of the tube with a mass of colour water. Or in other words, you get turbulence. So you get this nice visualization of what he saw. It kind of starts out a little bit straight, just like we saw before, but eventually kind of something happens and all of a sudden we get turbulence. So we'd really like to know what that something actually was. But surely this is really just the same story as a cylinder. I just take my fluid and I just make it go through faster, and then I get turbulence. So we solved it, right? Well, probably not quite. It turns out there are a few other factors involved as well. So As part of that experiment, he experimented with fluids of different viscosities. So if you tried this experiment with something like treacle, which is a lot thicker than water, or it has this more viscous effect, to be more precise, the same speed wouldn't, using the fluid at the same speed as the water, wouldn't make it turbulent. So the fluid's viscosity is important. So a little demo of viscosity, you can imagine something like water that's on the left-hand side here, and maybe something like golden syrup or treacle or some really viscous fluid on the right-hand side here. And that viscosity is very important in determining when the flow could transition to turbulence. Similarly, he found if you make the pipe smaller in diameter, you have to make the fluid faster to make it turbulent. So that implies that the length scale is important too. So after a lot of experimentation, he's basically identified the 3 critical parameters that are involved in making the fluid go from laminar to turbulent flow. He's got the fluid velocity, the diameter of the pipe, and the fluid's viscosity. And then if you play around with those numbers, eventually you'll stumble upon this, which is called the Reynolds number. And this will be the only equation in the entire presentation, I promise you. It's not really even an equation, it's just a way to calculate a number. So if you take the fluid velocity, and then you multiply that by the diameter of the pipe, and then you divide by what's called the kinematic viscosity, which is essentially just a measure of the viscosity of the fluid, then you get this number which doesn't have any dimensions like meters or seconds, which is called the Reynolds number. And what he showed in that original paper of his is that the Reynolds number determines when the fluid's laminar and when it's turbulent. And if you go ahead and you look at something like cylinder flow, for example, because the Reynolds number applies there too, the D in this case, instead of the diameter of the pipe, is the diameter of the cylinder, you can look at different values of Reynolds numbers from very low ones through to very high Reynolds numbers, and you can see the transition happen in terms of laminar flow. And you can try this with all kinds of different diameters of pipes and velocities and viscosities of fluids, and you'll always find that this kind of behavior holds. So this was probably a seminal work in our early understanding of fluid dynamics. Okay, so now we have this magical Reynolds number, we must really be done now, right? Well, actually, there's probably a little bit more work to do. In this case, by a bit, I mean about 135 years worth of work. So the thing that's kind of interesting about Reynolds' paper is that he sees that sometimes you get these things that are called turbulent flashes. So he actually used the light of an electric spark to visualize these things. And he's kind of drawn one of the things that he saw in that visualization there. This is really interesting because in those cases, the fluid isn't fully turbulent, but it also isn't fully laminar. It's what we might call intermittent. Some parts are laminar and some parts are turbulent. And so the natural question that you might ask yourself now is, well, I know that the Reynolds number controls when a fluid becomes laminar and when it becomes turbulent in some way, but what's the value of the Reynolds number? So if I have some Reynolds number somewhere in the middle, when's the fluid laminar and when is it turbulent? And that's really the critical question that's remained somewhat unanswered now for a very long period of time. So just to give some visual representation of that problem, imagine you've got this line and the line represents Reynolds number. So lower values of Reynolds number on the left, higher values are on the right. Reynolds said around about Reynolds number 2000, things start to change from being laminar into turbulent. And a lot of experiments over the years show that's actually the case. So we've all repeated Reynolds' experiment over and over and over again over the years, and we've shown that that's broadly true. So if you have a fluid that's less than the Reynolds number of about 2000 in a pipe, then it's laminar. If it's above 2000, then it's usually turbulent. The irritating thing for all of us who want a precise answer to that question is, well, in the middle here, you have this awkward region where sometimes the fluid is laminar and sometimes it's turbulent. So it's not like at 2001, the fluid's always turbulent, and at 1999, it's always laminar. Sometimes you can be at Reynolds number 1700 and the fluid's turbulent for a little bit. Sometimes you can be at Reynolds number 2500 and it'll be laminar for a bit. And that's a really frustrating question because we know that the Reynolds number has some relationship here, but we can't necessarily figure out what the problem is. So if you take engineering as your degree of choice, then one of the things that we might have you do is actually to reperform some of Reynolds' experiments in the lab.
So here's a typical setup. You've got your nice pipe on the left hand side, and we're going to let water flow out of the right hand side because that makes it easier for us to observe when the fluid is laminar and when it's turbulent, or at least it accentuates it. So you can see in this clip here, if we look carefully, there's this nice dye which is following one of the laminar trajectories here. But every so often, if you look carefully, you're seeing little flashes where actually the dye suddenly becomes completely uniform in the fluid. And that indicates there's a lot of mixing going on there. The dye's mixed into the fluid, and so it's become turbulent. You can also see that when the fluid exits the pipe, when it's laminar, it stays a lot higher than when the fluid suddenly becomes turbulent and starts to drop all of a sudden. So by actually measuring the height of the fluid as it comes out of the pipe there, you can actually work out things like the Reynolds number. So this problem really left scientists and engineers scratching their heads. And one of the things that we don't like in the scientific world is not knowing the answer to a specific problem. So for nearly 125 years, we kind of scratched our heads about this. And I was lucky enough at the time of my PhD to be working with a group of really talented researchers where we made a little bit of understanding as to what actually happens in this process. So I want to kind of walk you through that and kind of maybe give you an insight into more modern science that you wouldn't necessarily see in kind of undergraduate fluid dynamics textbook just yet. So here's a figure, and it might not be clear entirely what's going on from this, so I'm going to try and walk you through it. So on the horizontal axis, or the x-axis, what you're seeing is the length of the pipe. So you're kind of walking down the pipe as you walk down the horizontal axis. As in the vertical direction, as you go upwards, you are seeing what happens as a function of time. And the color that you see is like the turbulence intensity. So what we do here is we start off, in this case, a numerical simulation with one of these turbulent flashes right in the middle of the pipe, and just one of them. And we're going to run that at a couple of different Reynolds numbers. We're going to run it below 2000, and we're going to run it above 2000, and we're going to see what happens. Now, when you run below 2000, what you see is that essentially turbulent flash there is going to run out of steam and relaminarize. And the laminar fluid in this case is denoted by the black color. So this isn't entirely surprising. We know that sometimes these things decay, but what we didn't necessarily know about so much was that, in fact, sometimes the opposite is true, and sometimes those turbulent flashes spread. So in the right-hand figure, what you're seeing here is the Reynolds number up a little bit. We're running at Reynolds number 2350 here, so that's above that 2000, magical 2000 number. And what you can see is that as this thing proceeds in time, these flashes start to spread. So if we kind of zoom into this figure a little bit so we can see what's going on, what I'm going to do is take cross sections through the pipe at different times so you can see what these things look like. So here's one by itself when it starts. That's just a single little turbulent patch by itself. And so now you're seeing the fluid in a cross section of the pipe. So you can actually see the turbulent flash itself. So if we fast forward the simulation a little bit, and it really is a little bit in this figure, what we can see is that turbulent patch, because at Reynolds number 2350, there's more energy being pushed through that turbulent patch, it starts to grow. And eventually, if we wait long enough, what we'll see is that that will split into two. And in fact, if you go ahead and then you start to look like for longer and longer times, you can see in this figure that that patch itself is going to split into two itself. And eventually it's going to spread so that it fills the entire pipe. So that's really important because that seems like some kind of way that we could identify a mechanism by which at least most of the pipe ends up being turbulent, if not all of it, in the long run. So ultimately what we found out is that the transition and what determines it is not just the splitting process or just the decaying process. It's actually the balance between those two things. At some point you reach some equilibrium, some stopping point where the rate at which things decay equals the rate at which things split, and that allows us to determine a precise point at which we can say that's the transition point. So we went ahead and we did that. We measured lifetimes of these things. So if you consider one of those turbulent flashes by itself, you can measure the amount of time for different Reynolds numbers that it takes for that thing to either decay or to spread. And if you do that a whole bunch of times, and I do mean a whole bunch of times, you can draw two curves, which you can see on this figure. And on the left-hand side, you have decaying turbulence. On the right-hand side, you have the spreading turbulence. And where those two curves meet in the middle dictates the transition point. And if you look at where that is, that's about Reynolds number of 2040. So in the end, it ended up being pretty close. But the important thing is to actually understand a little bit more about what happens in pipe flow. So before I finish, because our time is cracking on here, I did want to say pipes are pretty easy after all, but really we'd like to know about more complicated cases too. So what about more complicated real world type cases? Well, since I did that research, I've moved on to look at some of those things. And in particular, I rely a lot on computational power, the same kind of computational power that I used with the pipe flow problems. And so my current research aims to use supercomputers of thousands or tens of thousands of processing cores and develop the fluid dynamics software, the same stuff actually that I used on the pipe flow cases, but now expanding it out to solve really challenging aeronautical problems. So to give you a flavor of the kind of things that you could do with this and get more insight to turbulence through some of those routes, here's some aeronautical problems. You see on the left-hand side, and on the right bottom side, there are some typical Formula 1 type cases where we're kind of looking to optimize downforce and improve the performance of the car. In the middle is a kind of classical aeronautical case where you've got one of these really, really strong wake vortices that we saw earlier, and we'd like to be able to predict how that vortex tracks downstream and how it interacts perhaps with other vortices. And in the top right, we've probably the largest simulation that I've done to date, which is the track car that I showed you earlier. And you can just see the amount of complex structures that we have in there. So we've gone from a very, very simple pipe to some very, very complicated objects too. And although I don't have time to really delve into that, a lot of the things that we can learn about things like pipe flow and channel flows and the simpler canonical cases can help us to inform our design of those things too. So, in conclusion, turbulence is pretty hard. Even after 125 years, we only really learned about transition in a pipe pretty recently and managed to really pin down what was going on there. Although it might not seem like it from this talk, though, we actually did learn an awful lot along the way. The discoveries along the way have definitely helped us to shape everything from designing really efficient golf balls, believe it or not, and you can go ahead and Google that, and that's a true story, through to Formula 1 cars and developing efficient aircraft. And the more that we work on this and the more that we understand turbulence, the better that we can understand those problems and develop next generations of aircraft, Formula 1 cars, climate modeling and prediction in order to advance our knowledge in all kinds of areas within science and engineering. So there's still an awful lot to do. And I hope this might really inspire you to go and take a look at some of the other topics related to fluid dynamics. I've left a few links in the additional resources for some other stuff that you can go and play around and work on. But with that said, thank you very much for your time and listening. And I really hope that you enjoyed this talk and all the other talks that we've got for you. Thanks very much. So in my talk, I mentioned computational resources quite a lot and the fact that I use computers to do a lot of my fluid dynamics simulations. And so my original plan before the whole coronavirus thing happened would be to get you into one of the labs in the university building and maybe run a few computer simulations. And of course, that's not possible anymore. But it turns out there are some really nice web-based utilities that you can use that I want to kind of share and go through really quickly and maybe get you started with to give you a demonstration how they work. So the first thing I want to show you is called SimScale. This is a free online website. You can go and sign up for an account, but everybody can by default have about 3,000 CPU hours of compute on this resource, which is really helpful for people such as yourselves that maybe just want to play around with this or do like some smaller simulations. One of the things you find about computational fluid dynamics is because of all the different scales that are involved, the simulations that I showed you are very, very expensive to run in general, and they can require hundreds and hundreds of thousands of hours of CPU time to run. So we're not going to try and be that ambitious here. We're just going to try and run some really basic demonstrations because this is actually fully fledged CFD software that you can run in your web browser. So if you sign up for a SimScale account and then you go in and have a look in the profile, the dashboard here, you can see that I have a few options. And if you go to the help option in particular, you can see the tutorials page. And this might be actually the first thing that you see when you sign up for an account there. So I'm going to click on the fluid dynamics tutorial. I'm going to get rid of that for a second. This is a really simple example. You can kind of click and drag here to move and navigate around here. And we've got a pipe, essentially. We've got a pipe that's got two inlets. So you have two connections here. You have velocity that's going to go in here, and you've got fluid that's going to come in here, and it's going to come out here. Okay. So I'm going to go ahead. I'm going to go and click create simulation here. And that's going to give me all these different options that I might be able to do. So there's all different kinds of flow choices here. I might have really complicated thermomechanical properties, or I might have compressible flows, all kinds of different things. And these are all obviously quite complicated, quite involved. So let's not do any of that. Let's just go straight for incompressible flow, which is like the simplest kind of fluid flow that you can do. So we'll click on that. We'll create a simulation from that. I've got a number of different options here. Now, we talked about turbulence quite a lot, and it turns out that turbulence is very expensive to model precisely because of all the scales that are involved and the time scales and length scales that we were talking about. So a cheaper way to kind of model those is to construct a mathematical model. And instead of actually simulating the full turbulent flow, we can model those features instead. And you can see here that I've got a turbulence model selected, and that's the one that comes up by default, which is this K omega SST. It's not important that you actually understand what's going on here, just the concept that we're modeling the turbulence. And we're not going to do transient simulation or a time-dependent one like I showed in the lectures, because again, it's just a little bit too long. We're going to do a steady state. So we're just going to compute the flow as if it were in an average state or a steady state. So I'm going to go ahead and just take all those default options and hit save. And then I've got some circles here, and those are the bits that I need to go now and fill in. So let's click on this materials section, and here I can choose the type of gas or solid, the type of gas or fluid that I want to simulate. In this case, let's just go ahead and choose water, click apply. And then you can see here that I've assigned water to my solid 1 volume here, which is this big blue volume. So that's the whole pipe. I'm saying, right, I want to use water within my pipe. So let's go ahead, click that save button. Now, what I have to do is specify what we call boundary conditions. So I have to tell my numerical solver where the fluid is coming in and where the fluid is going out and where the fluid hits a wall. So what we can do here is say, okay, let's add a boundary condition. Let's add a velocity inlet in particular. So now I have to tell the solver which way the fluid is going to flow through that face. Is it going to, and how fast it's going to flow through that face. So I know that if I look at this face here, I happen to know for this case that the y direction is like straight up. So if I specified a value of 1 meter per second here as the velocity, that would be quite fast, but it would be going in the wrong direction. That would be going directly upwards in this picture. I in fact want to do -1, which is going to take the fluid and push it into my pipe here. And then to tell it which face I want to apply that boundary condition on, I click the face, and I can see now that that face has appeared in here. And if I hover over here, then I can see in the picture which face that's associated with. So let's go ahead, let's save that velocity inlet, and let's go and add another one. So now we can do exactly the same for this face. I happen to know that this direction here, taking this face and looking directly opposite that face would be the Z direction, and that's the forward Z direction. So again, maybe I want a -1.5 for that direction, let's say. And again, I need to select that face so that it knows that that boundary condition gets applied to that face. So that tells the solver that I want some fluid coming in here, and I want the speed of the fluid to be 1 meter per second, and I've got some fluid coming in here, and I want the speed of that to be negative 1.5 meter per second. Okay, so we'll save that. Now I need to deal with this face. So the fluid is going to come in here, and it's going to come in here, and it's going to come out here. So in order to specify an outlet, I have to define what's called a pressure outlet condition. So I don't want to get too much into the details here, but it's basically specifying that to get the fluid to go from here, and in fact here to here, we have to say that there's going to be some pressure in the pipe. And the way that we impose the change in pressure is by selecting a pressure outlet here. So I'm going to go ahead, I'm going to select that pressure outlet. I can select what's called a gauge pressure of 0. You don't have to understand what that means at all, but essentially it's just a reference value for pressure. And I can just go ahead and click save. And that's basically the whole thing set up. It's a pretty simple case, but it shows you how you can do this actually from within your web browser, which I think is pretty cool, versus having to need some really specialist software that you might put on your computer. So let's go ahead, let's add a simulation run, and we're going to click start. Now this is going to take some time. The first thing you actually have to do is, well, you don't have to do it, but the computer's going to do it for you, is construct a mesh. So you've got to take this nice smooth looking surface here, and you've got to split it up into lots and lots of tiny little cells, because the computer really doesn't know how to deal with something that looks like this. We have to simplify things down a little bit, and inside each cell we can simulate the fluid and the fluid going in and out of the cell. So we simplify things by kind of breaking this guy up into lots and lots of different cells. And that's what you're seeing here. It's saying it's computing the mesh, and that can take a little time. So I'm going to pause for a second, and you're going to have a quick jump cut to when I get my mesh through. Okay, so I'm back. That took about a minute for me, or a minute and a half. So now it's updated here to say my job started, and in fact you can then see it's just blipped to 10% now to tell me that it's 10% of the way through running the simulation itself. So one of the things you're going to appreciate, hopefully, in doing all of this is that it can take quite a long time to actually run fluid dynamics simulations. So one of the things you learn as a fluid dynamics researcher is certainly to have quite a bit of patience, or perhaps to make an awful lot of cups of tea whilst you're trying to run these things. But essentially, if we wait long enough now, what we'll see is the results come in, and we can kind of visualize those results as the simulation is running. So I'm going to let this run for a little bit. I'm going to wait for this to transfer from a queued state, where it's just waiting to run, through to a running state, where there's actually been some resources allocated and now the job can run. And then once we're there, I'm going to come back and we're going to have a look at the results. Okay, so I'm starting to get to the point where I've got some results coming in. You see this has been running maybe about 3 minutes now. And if you click the little plus icon on here, you can actually see some of the things that have come in. So I'm going to click on the solver log. So here you can see all the technical stuff that's going on under the hood. That's not really important for the purposes of what we want to look at. But you can also look at these convergence plots, which are quite nice. So these will update as the solver progresses. And basically you want these things to get down to a nice steady state. So we're not quite there yet, but we can start to at least look at some of these results. So let's go ahead and click on solution fields. And when you do that, it's going to go ahead, open this results up, and you're going to get a new visualization here, which is going to allow you to actually see the results, which is pretty cool. So down here, you can actually see a little box that's got the X, Y, and Z directions on it. And if you like, you can click on one of those so that you can see the pipe from a particular angle. So what I'll do is I'll go ahead and make a slice through here so that we can start to see what the solution is starting to look like. So to do that, I'm going to add a cutting plane here. And the cutting plane is exactly what it kind of says. It's a cut through a plane. And to make it cut through, you can see in this case, it's selected the Z direction for me, which is this direction here. I'd like to take a cut across the whole pipe so I can see the whole cross section of the entire thing. So what I'm going to do is, well, that's the X direction there. So I'm going to choose this guy to be normal to the X direction. And looking at that, actually doesn't look like anything's come in yet. So I'm probably going to have to wait a couple of minutes for something to come in. Once the simulation starts to update, then I can start, then a little box is going to appear down here that I can click on to update. And I'll show you that once the simulation is updated a bit more. So I'm back after a little while. I see that the convergence plot is now starting to have quite a lot more data in it. So you can see that my time in seconds here has increased quite a bit. I'm now up at 120 seconds or so. And if you want to see the updated solution fields, it'll show you a box occasionally. But if not, what you can do is click on these 3 right arrows here. These 3 lines here, and then hit the reload results button here. So when you do that, it'll pull all the latest data so you can have a quick look at it. So now if I look at my plane here, I actually have some data now, and I can start to play around with this. So I could, for example, this is showing me the velocity in the X direction. So that's showing the velocity in that direction. But I might want to look at where the turbulence is being generated the most. So to do that, let's look at this K field, or sorry, this K field here. If I hit that, I can see I've got this big red patch in here of turbulence being generated. And that kind of indicates to me that something's going on in this region where turbulence intensity is very high. And actually that kind of makes sense, because you can imagine as the fluid is coming down here, it's going to meet the fluid that's coming in here. And so any fluid that comes in here, which isn't moving in that direction, it's going to get caught by that current and start to kind of swirl in that direction. That's why we end up with this big region of turbulence being generated. So this is actually a really nice way of being able to visualize what's going on here. And you can imagine if this was a little bit more complicated, we might then try and redesign the shape of this thing so that we kind of gradually introduce this new velocity from this direction so that we don't have this big intense area of turbulence generation here. So another thing I might want to do is actually seed some little particles and let the particles flow along the path that the fluid sets out for me. So like I showed you in the slides where you have the streamlines, we can visualize these in the simulation results. So I've got some new data, so I'm going to go ahead and reload that. And now I have that, I'm going to click on particle traces here. And that's going to kind of hide most of the domain here, but it's going to still show me the inlet and outlet, so I can select different parts to put particles within. So let's let's just generate some seeds. So I'm going to use maybe 20 seeds in each direction here. It's going to be clear what actually happens here in a second, but I'm just going to generate some seeds. Oops. I'm going to go back here, click pick, and then click on my inflow here. And you can see when I do that, it generates these seeds so that I can, and then creates a particle at that location. And so what you can see here is that those particles kind of come in from that inflow area here, and as soon as they meet the ones from here, they start to kind of dip down. You can really clearly see that just here. So this is where the flow is kind of getting diverted by the flow that's coming in here. So you might actually want to reduce these a little bit so that you get, you know, fewer in that direction, and it's a little bit easier to see kind of what's going on. Or maybe increase the spacing between them, and then you can really see where those particles are being generated. If you want to kind of color them a little nicer, then what you can do is select in the map scalar thing here, you can select pressure, and that will show you the kind of drop in pressure. So you start at this high pressure and you end up at this very low pressure here. So let's do the same thing. Let's add another particle trace now, and let's do the same thing for this pipe here. So we can go ahead and click the pip button this time, which I forgot before. We can add some particles in there too, and then again let's maybe color that by the pressure. So there you get kind of a really clear view of what's going on in the fluid itself, and you can see, you know, playing around with this, you can really get a very clear view of what happens in the fluid dynamics here. That particles are coming in here and they're kind of mixing with the particles that you see here, and as a result of that, you end up having this region of turbulence that we saw in our visualization there before. So I'd really encourage you to go ahead, have a play around with some of these options. It doesn't matter if you don't understand absolutely everything that's going on. It's really important just to maybe try and get a feel for things, and you know, just play around with increasing the velocity or decreasing the velocity, play around with maybe changing the material that you're putting through. Instead of water, maybe try and use something else, and just have a general mess around with this. And when you're kind of fed up with doing that and you've messed around to your heart's content, maybe go ahead and click this public project section here. I think this is really one of the nicest things about this platform, because it allows you to view all the other projects that people have been working on in a collaborative way. So for example, you've got this really nice project here where you've got the Toronto Four Seasons Wind, or you've got this Tesla Cybertruck aerodynamics project here. Maybe we can take a bit of a closer look at that one. So if someone's been looking at the aerodynamics of a Cybertruck, they have a pretty distinctive, and I would argue perhaps somewhat unaerodynamic shape. So let's go ahead, maybe open that one up, and then you can see from in here that we have the model to play around with. We have the simulation runs that this person has run, and then we might be able to go ahead and look at some of those. So do play around with the platform. As I said, you've got quite a lot of CPU time, so 3,000 or so hours. If you really want to get seriously into this and spend a few days messing around with it, if you really want to. But if not, maybe just go and click around and have a look at some of the projects that other people have run. I hope you found that useful, and certainly hope you enjoy playing with that software.